Hey everybody, welcome back to Calculus. Today we are going to be talking about continuity. So let's talk about a continuous function. Let's talk about what a continuous function is. A function f is continuous at every number a if and only if the limit as x approaches a of f of x equals f of a. This requires that f of a has to be defined and the limit as x approaches a of f of x has to exist. So for example, if we want to know if our function is continuous at a number 5, for example, it should be that the limit as x approaches 5 of f of x should be f of 5. So a function f is continuous on an interval if it's continuous at each point in that interval. And essentially all polynomial, rational, root, and trigonometric functions are continuous everywhere in their domains. If f and g are continuous at a and c is constant, then the following are also continuous at a: f plus g, f minus g, c times f times g, and f divided by g, but g of a cannot be 0. If g is continuous at a and f is continuous at g of a, then the composite function f composed onto g, which is given by f of g of x, is continuous at a. That's what that open circle between f and g are. It means composed onto. So we also need to talk about discontinuity and what it means to be discontinuous. So if f is defined near a, except perhaps at a, we can say that f is discontinuous at a if f is not continuous at a. We can also say that f has a discontinuity at a. So when talking about discontinuity, there are 3 types of discontinuities that we want to look out for. There are there's the removable discontinuity, which is a discontinuity that can be removed by redefining f at just a single number. It will look like a hole in the graph, as you can see by the graph marked number 1 in the bottom left-hand corner there. There's also the infinite discontinuity, which is another name for a vertical asymptote, which is the middle graph there. And then there's a jump discontinuity, which is any discontinuity that isn't removable or infinite. You'll notice that the function jumps from one value to another. So if we go to the removable discontinuity here, you can see that we have this open circle hole in the graph, and then there's another point right here where the function is defined, but it's just not defined at that. It's not continuous because you can't basically draw a straight line through it. It goes up to this point right here, and there's a hole in the graph down here. As for this jump discontinuity here, you can see that as you go along the graph, it stops right here, and then it just jumps up to here. So that's how you would know it's a jump discontinuity. So when do these types of things happen? Removable discontinuities typically appear when a function has a value 0 over 0 at a certain x value. And you can usually simplify these by getting rid of the, you can usually simplify the function to get rid of the removable discontinuity. Infinite discontinuities typically appear when a function has a value of a non-zero number over 0 at a certain x value. And jump discontinuities typically appear in piecewise defined functions. Now we get on to the intermediate value theorem, which is a very important theorem and you're going to have to memorize it, so I would suggest you memorize it as soon as possible. But the intermediate value theorem says, suppose that f is continuous on the closed interval a to b, and let n be any number between f of a and f of b, where f of a does not equal f of b. There exists a number c in the interval a to b, and that this symbol in between c and this interval, this symbol it means inside of. So there's a value c that's within this interval a to b, such that f of c equals n. So in order to demonstrate that a little bit more clearly, I drew out this graph here, and you can see I have my point a, and it's f of a up here. So we have this a f of a ordered pair, and then we have a b f of b ordered pair here. And I'm saying if there's a value c that's in between a and b, then that must mean there's a value n such that f of c equals n, and it's in between f of a and f of b, because n has to be between f of a and f of b. In other words, a continuous function takes on every intermediate value between the function values f of a and f of b, and this probably seems abstract and confusing right now, but I think once we get into the practice problems, it's going to hopefully make a lot more sense. So let's get into those practice problems. Okay, so in this next question, we are asked, from the graph of f, state the numbers at which f is discontinuous and explain why. And this is the graph we're given. As you can see, it's a piecewise defined function that's defined in 4 intervals. So let's just go left to right for this. So the first thing I see that's not continuous is f of negative 4 right here. And the reason it's not continuous is because there's a removable discontinuity there. So I'm going to say RD for removable discontinuity at f of negative 4. Like that. The next discontinuity I see is at f of negative 2. You can see there's a jump discontinuity here. The limits are, the two-sided limit does not exist. The limit as x approaches negative 2 from the left-hand side is this value right here, and the limit as x approaches negative 2 from the right is this value right here. So I'm going to say JD for jump discontinuity, JD at f of negative 2. The next thing I see that is discontinuous is f of 2 right here, and it's the same reason. It's a jump discontinuity. So I'm going to say that that is also a jump discontinuity, so I'm going to say comma f of 2. And then so the next discontinuity I see is at f equals 4. So the reason f equals 4 is a discontinuity is because the two-sided limit, once again, does not exist. The limit as x approaches 4 from the left side goes way down here. I don't know if it goes to negative infinity or not. The graph doesn't show. So I can't confidently say that it's a vertical asymptote because it doesn't show that it goes down to negative infinity. And then the limit as x approaches 4 from the right is this value up here. So I'm going to say another jump discontinuity at f equals 4, or f of 4. And that's how you would do that one. So in this next question, we are asked to use the definition of continuity and the properties of limits to show that the function is continuous at the given number a. So remember, our definition of continuity is that the limit as x approaches a of f of x should equal f of a. That's how we prove that a function is continuous at a number a. And the function we're given is x plus 2x cubed, and all of that is raised to the 4th. So what I'm going to do is I'm going to first do f of negative 1, and then I'm going to do the limit as x approaches negative 1 of f of x. So let's start with f of negative 1. F of negative 1 is going to be negative 1. I'm just going to plug in negative 1 wherever I see x. So it's going to be negative 1 plus 2 times negative 1 cubed, and all that's going to be raised to the 4th. So that gives me negative 1 plus 2, and negative 1 cubed is still negative 1, so it's just negative 1, and it's all still raised to the 4th. So that's negative 1 minus 2 raised to the 4th, which is negative 3 raised to the 4th, which is 81. Now I'm going to do the limit as x approaches negative 1 of f of x. So that will give me the limit as x approaches negative 1 of x plus 2x cubed raised to the 4th. Now, I don't have any situation here in which I would have a discontinuity. This is a polynomial, remember, which means it's going to be continuous at every number in its domain, and negative 1 is in the domain here. But just to make sure, I'm going to directly substitute negative 1 wherever I see x. So that's going to give me -1 plus 2 times -1 cubed raised to the 4th, and you can see that that's just that step right there. So we can continue going down this way like that. We would just copy all these steps until we get to 81, and that's how we'd show it's continuous. So that's how you would do that one. Okay, so in this next problem we're asked to use the definition of continuity and the properties of limits to show that the function is continuous at the given interval. And our function is 2x plus 3 over x minus 2, and our interval is 2 to infinity. So remember from our properties of limits and our definitions of continuity that a rational function like this is continuous everywhere in their domain. So we want to look where, we want to find out the domain basically. And the domain for this is we're asking ourselves what number can we plug in for x, and we get an answer out of it. The only number we can't plug in for x is, and this one is 2. Once we plug in 2, then we would have a 0 in the denominator, so x cannot equal 2. In other words, this is continuous from -infinity to 2, and that's a closed interval, and then 2 to infinity, and that's a closed interval. So you can have 2.000001, you can have 5 million, you can have -1 billion. You just can't have the number 2 in here. And if we look here, we said it's continuous on 2 to infinity, and the interval they're asking about is 2 to infinity. So right there we've just proved that it's continuous on that interval. So that's how I would do that problem. Alright, so in this next problem we are asked to explain why the function is discontinuous at the given number a, and then we're asked to sketch a graph of the function. So the function we're given here is 1 over x plus 2, and our a value is -2. So I'm actually going to graph this first and then explain why it's discontinuous second. So if I just draw a rough sketch here, and I have my interval, or I have my points here like this, so at 0, for example, x equals 0, our point will be 1/2. At x equals -1, our value will be 1, our y value will be 1. At x equals -2, however, it would be 1 over 0, undefined. In other words, a vertical asymptote right there. And then down here, or over here, at x equals -3, it would be -1. Y would be -1. Like this. Then if we continue over here, at x equals 1, 1 plus 2 is 3, so we'd have 1/3, and it would continue going on like this. So we would essentially have a graph that looks like this, and this area over here would look something like that. And we can see here that there's an infinite discontinuity here. There's a vertical asymptote, so that's why it's discontinuous. There's a vertical asymptote. I'm just gonna write VA to abbreviate. There's a vertical asymptote at f of -2. So that's how I do that one. Okay, so in this next problem we're asked the exact same thing, except our function now is different. Our function now is piecewise defined, and one piece is that f of x equals 1 over x plus 2 when x is not equal to -2, but it's equal to 1 when x is equal to -2. So let's go ahead and sketch the graph, and I'm just going to draw out the little pegs like this. They're not going to be perfectly even, but the point will still hold, I think. So let's start where x does not equal -2. At 0, we'd have 1/2 again. At 1, we'd have 1/3, and we'd continue on like that. And then at x equals -1, we'd have 1 over 1, like this. At x equals 2, or at x equals -2, it would just be 1 again, so like that. And then at x equals -3, it would be 1 over -1, which is just -1 like this. So we can see that we we'd have a graph that goes something like this, and it looks something like this. And we'd have an open circle here as it gets closer and closer to -2, but then as it reaches -2, it jumps down to here. So the reason why this function is discontinuous at the given number -2 is because there's a jump discontinuity, which I'll abbreviate as JD, at f of -2. And that's how you would do that one. Okay, so in this next problem we are once again asked to do the same thing, but again we're given a different function. This time our function is defined piecewise, but it's defined in 3 different pieces this time. The first being cosine of x when x is less than 0, 0 when x is 0, and 1 minus x squared when x is greater than 0. So I'm going to go ahead and make a graph here. And I'm going to go ahead and make my plot my pegs here. So at I'm just going to start off with the easiest one. At x equals 0, we're at 0. Now, as we know from the cosine graph, it starts off at 1. Cosine of 0 is 1. So I'm going to put that there, but I'm going to put it at an open circle to indicate that it does not include 0. It would just approach 0. And then as we get to -pi, which would be -3.14, so probably like right here-ish, it would start to get down to -1. So it would look something like this. That's a very rough sketch of cosine, but you get the point. And then 1 minus x squared whenever x is greater than 0. So at 0, once again, this would be 1 minus 0, which is 1. So we'd have another open circle on 1. And then at x equals 1, 1 minus 1 is 0. And then at x equals 2, 1 minus 2 squared is 1 minus 4, which is -3. And it would look like a downwards opening parabola like this. So we can see now that there is a removable, it would actually be a jump discontinuity here. It would be a jump discontinuity because the value jumps down to 0 once you get here. The reason it wouldn't be a removable discontinuity is because you can't simplify this piecewise defined function any further. So I'd say there's a jump discontinuity at f of 0. And that's how I would do that one. Okay, so in this next problem we are asked to explain why the function is continuous at every number in its domain, then state the domain. And the function we're given is 2x squared minus x minus 1 over x squared plus 1. So this is continuous at every number in its domain because it's a rational function. And we know that rational functions are one of those functions that we listed earlier that are continuous at every number in its domain. So now we should state the domain. And basically what we're looking for is any number that would make the denominator equal to 0. And you can see after probably a little bit of time looking at the denominator that there's no number that does this. And we can prove that the denominator can't be equal to 0 by setting it equal to 0. X squared plus 1 equals 0. Then we subtract 1. Then we have x squared equals -1. And in order to get rid of a square, we take the square root. And we have x equals the square root of -1, which is an imaginary number. Meaning that our interval would be -infinity to infinity. There is no number to make the denominator 0. So that's how I do that one. Okay, so in this next problem, we are once again asked the same thing, except our function is different. Our function now is the cube root of x minus 2 over x cubed minus 2. Now as we can see, all we have is a root function, a cube root function in fact, a root function over just a exponential function, a cubing function. I'm just going to write cubing function. And this together is just a rational function still. It's still a rational function. So that's why it's continuous at every number in its domain. And when talking about the domain, I'm once again going to set this equal to 0. I'm going to have x cubed minus 2 equals 0. Add 2 to both sides. X cubed equals 2. Then I take the cube root to get rid of the cubing, and I get x equals the cube root of 2. So its domain would be negative infinity to cube root of 2, union cube root of 2 to infinity. And the reason I can include negative numbers in this is because this is a cube root on top. And a cube root is different from a square root in that with a square root you can't have a negative number underneath the radicand, but with a cube you can. So that's how you would do that one. Okay, so this next problem we're once again asked to do the same thing, just a different function. So now that I've done some of them, I want you to pause the video, try it on your own, and come back to it and see how you did. So assuming you've paused the video, let's do the problem and see how you did. So this function we're given is cosine of 1 minus x squared. This is a trigonometric function, and as we know from earlier, trigonometric function is continuous at every number in its domain. So I'm going to say it's continuous at every number in its domain because it's a trig function. Then state the domain. Well, a cosine, you can just plug anything in for it. Yeah, it's really as simple as that. You can plug in anything for x and you would get an answer out of it. The answer would probably be between 1 and negative 1, but you can plug anything into it. For example, if we plug in 0 for x, cosine of 1 minus 0 is just cosine of 1, which is a decimal number, I believe. I have my calculator right here so I can check. Cosine of 1 is 0.54. You can even plug in 50 for x, and you can do cosine of 1 minus 50 squared, and we can see what that is. That's negative 0.13. So you can test this out with a graphing calculator of your own, or a regular calculator of your own, in fact. So the domain is all real numbers, which is the same thing as negative infinity to infinity, basically. So that would be my answer to that one. Okay, so in this next question we're asked to do the exact same thing. Our function now is f of x equals the square root of 1 plus 1 over x. So this is continuous because it's a root function, and as we know from earlier, root functions are continuous at every number in their domain. So as for the domain, let's see what the domain is. So the first thing I'm going to look for is any number that would make this fraction here undefined, and that would be 0. So x cannot equal 0. And the other thing I'm going to look for is any number that would make this square root, or that would make these numbers under the radicand negative, because then we have a square root of a negative number. So you may think that, for example, negative 5 or negative 10 might be numbers you can't plug in because those seem like they would be large. It would make the number under the radicand negative, but that's not actually the case, because if we plug in negative 5 for x, we'd get 1 minus 1/5, which is a positive answer. However, if we go to x equals negative 1, we get 1 minus 1, which is 0, and then any number between 1 and 0 would also be would also result in a negative number under the radicand. So for example, if we had negative 1/2, we'd have 1 plus 1 over negative 1/2, which is the same thing as 1 minus 2, which is negative 1, and we'd have a square root of negative 1. So we can't have anything between negative, we can't have anything between negative 1 and 0, but we can have negative 1. So we can include negative 1, but we can't include 0. And then after that, any number greater than 0 will be positive, so we can have all those 0 to infinity. So when we're stating the domain, I can say negative infinity to negative 1, closed interval, union 0, open interval, to infinity. And that encapsulates these ideas in interval notation. So that's how I would do that one. Okay, so in this next question we are asked to use continuity to evaluate the limit. And the limit we're given is the limit as x approaches 4 of 5 plus the square root of x over the square root of 5 plus x. Now, I can just directly substitute 4 in for x because it's not going to equal 0 in the denominator. We're not going to have any problems as far as that's concerned. So I'm just going to directly substitute 4 for x. So I'm going to have 5 plus the square root of 4 over square root of 5 plus 4. Now, square root of 4 is 2, so I'm going to have 5 plus 2 over square root of 9. So 5 plus 2 is 7, and the square root of 9 is 3, so that's just 7/3. So that's how you do that one. Okay, so in this next question, we're asked the exact same thing, except our limit is different. This time our limit is the limit as x approaches pi over 4 of x times cosine squared of x. And once again, I can just directly substitute in pi over 4 for x. So that's what I'm going to do. And I'm going to get pi over 4 times cosine squared of pi over 4. Now, cosine of pi over 4 is square root of 2 over 2. So I'm going to have pi over 4 times square root of 2 over 2, and that whole thing is going to be squared. So then when I square that, square root of 2 squared is just 2, and 2 squared is 4. So I'm left with 2/4, which is the same thing, if we simplify, it's the same thing as 1/2. So I have pi over 4 times 1/2, which is pi over 8. So that would be my answer for that one. Okay, so in this next question we are asked to show that f is continuous on the interval infinity to negative infinity, and we're given the piecewise defined function f of x equals x squared when x is less than 1, and it's equal to the square root of x when x is greater than or equal to 1. So what we need to prove is that each of these pieces are continuous in their whole interval, and then we need to prove that they would basically be the same value at 1. Because if they're not the same value at 1, then it wouldn't be continuous at 1, and it wouldn't be continuous from infinity to negative infinity. So if we look at x squared, that's going to be x is less than 1. So that's going to be our negative infinity to 1 interval, basically. So we know that x squared is a polynomial, which is defined at every number in its domain. So there's nothing in the set there's nothing in the interval negative infinity to 1 that would make x squared undefined. So we know that yes, x squared is continuous from negative infinity to 1. Then if we look at square root of x, we're going to be looking at 1 to infinity. So square root of x is a root function. We know that it's defined on its interval, or it's defined on its entire domain. It's continuous and defined on its entire domain. The only numbers that are not in its domain are where x is less than 0. So -1, -3, -300, all those are not defined for this. We'd get an imaginary number. However, those numbers aren't in this piece. This is greater than or equal to 1. So this is 1, 3, and 300, and every number from 1 to infinity, basically. So we know that yes, it's defined and continuous there. So now we just need to make sure that these are the same values at 1. So at x equals 1, 1 squared is 1, and the square root of 1 is 1. So they're both equal to 1. So that's how you show that f of x is continuous from infinity to negative infinity. Okay, so in this next problem we are asked to find the numbers at which f is discontinuous and then to sketch the graph of f. what I'm going to do is I'm going to sketch the graph of f first, and then that's going to allow us to see where f is discontinuous much easier, I think. So I'm just going to draw a rough graph here, and I'm going to mark out my points here. Okay, so at x equals 0, that's going to go to this first interval here because 0 is included. So that's going to be 1 plus 0 squared, which is 1, like that. And this interval goes for as long as x is less than or equal to 0. So at x equals negative 1, 1 plus negative 1 squared is 1 plus 1, because negative 1 squared is 1. So 1 plus 1 is 2, like that. And then any other thing would go off the graph, I believe, because 2 squared is 4, and 1 plus 4 is 5, and that's not on the graph. But suffice it to say that this would look like a parabola like that. So then we have the next interval here, which is from 0 to 2, including 2, but not including 0. So 2 minus 0 would be 2, and I'm going to mark that out with an open circle just to show that this graph, this piece of the graph goes up to, but not including 0. Up to 0, but not including 0. Then at x equals 1, 2 minus 1 is 1. And at x equals 2, 2 minus 2 is 0, like that. So we'd have a linear line going like that. And then for x is greater than 2, at x equals 2, we would have 0 again, because 2 minus 2 is 0 and 0 squared is 0. So I'm going to draw an open circle around the closed circle, and then at x equals 3 right here, 3 minus 2 is 1, 1 squared is 1. And then at 2 here, at 4 here, 4 minus 2 is 2, and 2 squared is 4, so that would be somewhere up here. And that would look like another parabola, like that. So we can see now that there's a discontinuity at f of 0. There's a jump discontinuity at f of 0 because it just jumps. If we go from the right here, it jumps from 2 to all the way down to 1, and if we're going from the left here, it jumps from 1 to 2. And so that's how you would do that problem. The reason why there's not a discontinuity here is because they're both approaching the same value regardless. So the only discontinuity is at f of 0. So in this next question, we're once again asked to graph the numbers at which, find the numbers at which f is discontinuous and sketch the graph of f. The function we're given this time is also piecewise defined, but it's defined differently now. It's defined as x plus 2 when x is less than 0, 2x squared when x is greater than or equal to 0 and when it's less than or equal to 1, and it's defined as 2 minus x when x is greater than 1. So once again, I'm going to start by graphing this out, and that will give us a better idea of what we're dealing with as far as discontinuities are concerned. We'll be able to see where the discontinuities are more clearly than if we were just looking at this equation up here. So let's start at 0. So that would be this middle one right here, because it's defined as being x is greater than, or it's defined as 2x squared when x is greater than or equal to 0. That's what I'm trying to say. And when x is less than or equal to 1. So at 0, 2 times 0 squared is 2 times 0, because 0 squared is 0, which is just 0. At 1, 1 squared is 1, and 2 times 1 is 1, or 2 times 1 is 2. So it's like that. And our graph would look like this. It should be a little bit more curved though, because this is a parabola. So it would look like that. Then we go into the negative portion of the graph, and that would be this top piece right here, because it's defined when x is less than 0. So at x equals 0 though, 0 plus 2 is 2, so I'm going to draw an open circle at 2. And then from there, because we know it's linear, and the slope is 1, we can go down 1 to left 1, like this. And we can do that all the way until we reach the end of the graph right here, like that. And then for x is greater than 1, we have it being defined as 2 minus x. So at x equals 1, 2 minus 1 is 1. So at x equals 1, we have this open interval right here, because 2 minus 1 is 1. And once again, this is a linear equation right here, 2 minus x, with a slope of negative 1. So we can go down 1 over 1, down 1 over 1, down 1 over 1 again, and down 1 over 1 again. And we'd get this graph right here. So we can see from this that there's a discontinuity at f of 0. There's a jump discontinuity there. And then there is also a jump discontinuity at f of 1. It's not a hole in the graph because we can't reduce this, but it is a jump discontinuity because if we go from the right here, it jumps from 1 to 2, and if we go from the left, it jumps from 2 to 1. So that would be your answer for that one.